I highly recommend I highly recommend the book to anyone who has like an interest in neuroscience. And since talking about an object as complex like brain can be, it's like writing an encyclopedia, but I will focus on my like notes on what I know now that I didn't know before reading the book, and a brief introduction about it. So this is like I need to made it in 20 minutes, so I focused on some interesting things which can give a understanding and facts in like neuroscience research. So this is the layout, like a quick background, then what is spike, how spikes are generated, spike failure, dark neurons, and how spikes encodes its information. Now, then experiments and methods in neuroscience, then role of spikes in decision making, then some myths, and what are the open questions for research in human brain. So, starting with a quick background. So like human brain is very complicated, and we have around like 86 million of neurons in adult human brain. 1/4 of those neurons are in the cortex, and while 3/4 of them are in the cerebrum. Now, each neuron on an average connects to 75,000 other neurons. So this was like new and shocking to me, because most of the illustrations in the neuron book can make you believe that neurons perhaps make a maximum of 10 connections. And these all neurons are communicating by sending electrical spikes. So if you can say like each neuron is a computer, and your cortex contains around 17 billion of computers. And now there are many regions in human brains. So if you see in the diagram, so the frontal lobe is responsible for smell, speech, concentration, planning, problem solving, motor control, and the other regions are responsible for other daily activities which we are doing in every day. So let us take an example that you are in an office and someone bought a like packet of cookie and placed in an open area to enjoy. Now you will think that should I take that cookie or not? Now, if someone is health conscious, so he will think that how many calories? If someone is looking at me or not? Those other questions. So in those few moments, like your brain is burst with electrical energy, which generates a lots of spikes. Now, spikes are how neuron talks with them. So human brain is the most complex, sophisticated, and energy efficient computing system, and it it relies through the interaction and communication among the neurons. So the primitive processing units which transmit information between through the using the action potentials are spikes. So it is like a well-known sensory information, how spike patterns do. And we can say that spike is an electrical journey that information takes as it passes into your eyes and through your mind, and ultimately lead us to act. So spikes is all we are seeing, hearing, planning, playing, etc. So our brain largely depends on these electrical charges for all the activity. On an average, human brains consume like 80% of energy to generate that electrical spikes, which helps neuron to connect to other neurons. So but in the primitive animals, like early layers of our visual system don't use spikes. They communicate via simple diffusion of voltage. Like in the chemistry, there is an concept of diffusion of ions, if you can relate. So this information was like new to me, as I thought all neurons communicate via action potential. So the next is like how spikes are generated. So one spike is not dependent on only one neuron. To reach a threshold value of creating a spike, hundreds of neurons are responsible. Now, brain neurons can transmit signals using a flow of potassium and sodium ions, which produces a electrical spike called an action potential. So after an action potential is generated, the pump resets the arrangement of sodium and potassium ions and back to the original position, so that there would be like new spikes. Now, there are different modelings available to analyze these spike firing patterns, like Hugsin Hunky, leaky neuron, and some other models. So let's say in this diagram, I explained about the Hugsin Hunky model. So this is the representation from that paper. So now, like there is a sudden increase in the action in the voltage, which lead to reach to a threshold and generate the spike. Uh, Now there are like two types of neurons that are excitatory and inhibitory. Excitatory and inhibitory. So roughly 90% of connections to a neuron are excitatory, while the other 10% are inhibitory neurons. But the inhibitory connections are stronger, which ensure that for any neuron, uh, excitation and inhibition are kept in like equal balance. So, but a neuron spike can have different level of impact for each of the thousand of neuron it connects to. The connection strength is modulated by the number of receptors and downstream neurons and the number of transmitter release. So neurons typically don't fire deterministically. For the some input, sometimes they would fire and sometimes they wouldn't. Because a neuron doesn't fire deterministically, to know what a neuron is coding, we have to look beyond just one activation spike. So we have to see patterns in a spike. So while analyzing those patterns, researchers have analyzed that there are spike failures. So our spike activity doesn't stop, but there are certain spikes which don't reach to an action potential and then falls. So in this image, we can see that on a stimulus, like when a stimulus is given to, then the neurons are fired, but it didn't reach to a certain threshold value and initiation for spike generation, and it failed. The computer and the brain also have similar like signal mode, if you can say. So if we can take an example of the transistors, which uses the discrete values like zeros and ones to represent the information. One means there is information and zero means there is no information. Similarly, it's with the like spike in neuronal axons. So it, let's say it is a digital signal which in the neuron either it fires or doesn't fires at a given time, and when it fires, all the spikes like approximately of same size and same shape. So like this can be helpful in reliable long distance spike propagation. So these all things like the spike failure have some advantages. So some neurons, like most of the neurons in our retina, are non-spiking, and their output is transmitted by electrical signals. So that can transmit more information than that can have spikes. So
Deepa, I had a question.
mhm,
Um, um, you know, we discuss type 1 perceptual activities and type 2 activities, and I am guessing that whether it is type 1 or type 2 activities, neurons are going to participate. And if so, um, uh, is every activity that we do in this kind of millisecond time frame? Because if it is taking a millisecond time frame to for one neuron to fire, and if the action takes a series of neurons to have communicated, and with such a dense a visual stimuli or some stimuli coming to human brain will lead to firing of many neurons, right? You said one neuron is connected with what, 75,000 other neurons?
Yes. Yes.
So that means that that spike will spread to so many part of the neurons, and some will fail, so the thing will die, spreading, but others will continue to fire. So
Yes.
any stimuli would mean that there will be massive, flow through the brain. And
Mm-hmm.
if you what is the minimum time to action and maximum time to action could be, thing could be just firing at a slow pace and deliberative action. But I'm just wondering, in perceptual activity, how fast the things would be, because humans do react within millisecond time, well, maybe microsecond, I don't know. I mean, how fast do we react to a moving object towards us, or if we are falling, our hand moves out, how fast that happens. So I'm just wondering how these things add up when a network of neurons are involved in any particular activity and stimuli. Was there any discussion of this kind?
So kind of discussion, like on the human consciousness, consciousness, and human actions. So this is discussed in the end chapter of this book, and he left that these all are like still an open question.
Okay.
Yeah. So the current models which they are analyzing is totally on animals, and it is stated in the book that still it is not possible to go inside a human brain and check out these things on a single neuronal pattern. Okay. Okay. So let me continue. So, like, one surprising recent discovery has been made is that on an average, neuron fires like 1 hertz frequency, and most of the neurons don't spike at all. This implies two things: that most spikes in the human brain are produced by a small percentage of neurons that spike at greater than 10 hertz, and neurons not spiking at all are called dark neurons, which I can explain in the next slide. So, about 10% of the cortical neurons, at least half of all the spikes recorded. Most neurons produce less than one spike per minute. So, the brain communicates using spikes. So, these neurons are not communicating anything to anyone. They are called dark neurons. These dark neurons were a surprise for me, but it makes sense. Like when we put electrodes into a brain to measure activity, there are like the biasing towards the active neurons. So if you calculate the activity, you will just collect all the active neurons in the brain. Like how we will ever detect the neurons that don't spike at all? So recent discoveries there are some modern methods have revealed that most neurons are silent most of the time. So the dark neurons of the brain are neurons which don't respond to any kind of stimulus tested. These are also called silent neurons and are related to the concept of sparse firing, which is believed by the researchers that it's the general principle of brain organization. Sparse coding means that a given stimulus only activates a small number of neurons, and other neurons are silent and doing nothing but consuming energy, similar to the concept of spiking neural network in computer science, where most activations are at zero at any given time. Now, what are these dark neurons for? So nobody knows, but neuroscientists guess that either they may be super specialized, fire only when you will hear any news about Bill Gates, or they may represent like spare capacity of learning new concept, and that can be used to when the brain needs to form new circuits to store new information. So like uh, yeah, so after lots of spikes, failure, and we can discuss like how spike encodes information. So spikes, after the failure of spikes, still brain is encoding information and helping us to react using that information. Failure of a spike, there is like gen with the help, like if there is a spike failure, so the network can be generalized and that can encode information. Now there are two types of neural encoding in brain that help neurons to save information. First is spike rate. So spike rate is means that whenever there is new information, then there are certain number of spikes are firing. But for any other information, there are no spikes at all. So if you consider an example of like somebody is moving left to right. So for coding that information, there are many spikes are fired. But if somebody is moving from right to left in the same experiment, so there is like no spikes at all. The other one is spike time coding. So this coding is like the time delay between the two successive spikes. So the a very good example is about our sensory system. Like if someone is having an accident and falls, but that pain he can feel later on. So our brain use both kind of coding to save the information. And like for example, like sensory organs use the spike time coding, while the cortex neurons to computation rely more on spike rates. Uh, Now, after talking about the spikes, I will talk about how these are recorded. So current work and state of art is depend upon the animal models. It is not practically possible to implant the electrodes in a normal human being and leave them for lifetime. So for analyzing the spikes and spike firing rates, different models are like different methods are available. Those are statistical methods, Bayesian methods. Now researchers are using machine learning uh, to these researches for analyzing and predicting the outcome and decision making. For example, in this picture, like rat wants to reach to the cheese. So now with if there is an EEG electrodes, so or chemicals, we can actually predict like which movement is he is taking for the reaching to the cheese, like there is a next right or the left by using machine learning. Um, so as we talked about the decision making prediction using machine learning in previous slide, let's more discuss about the like role of spike in decision making. Like how we are able to have like second reactions when there are so many connection and loops in brain. We wouldn't it like making decision is the complex by using all those spikes and it will take forever. But like from any of the motor actions, we are reacting instantly. Our brain instead in like actively predicting what's going on to be happen next and what senses communicate in the error between the brain's prediction and outside reality. So for many tasks in the brain, single neuron firing may not mean anything, but decision making is depending upon the encoding of several neurons together at a time. And those several neurons are representing that information as a task. So this idea is called population encoding, and it may enable few neurons to encode a lot rich of information. One benefit of population encoding is that it allows individual neurons to be non-deterministic. while collectively it is learning through the feedback loops and enabling the network to encode the stable information. And one such example is that what if a neuron doesn't fire and the circuit have another connected neuron fire? It doesn't mean that a neuron doesn't fires and the whole circuit is failing, but they are using the other connections to taking the decision. So the decision which we make every day is relying on processing continuously refreshed streams of uncertain information. The information like choices, our actions on and on like upon which we made the decision. Let's take an example that people who are addicted to tea and coffee. So after waking up, can you think like how do you reach to that decision? Doing first thing in the morning. So these neurons are fired before doing that task and reaching to the kitchen and start preparing it. Now, this information developed over the time and encoding using several of the spikes generated doing in the initial time. So clearly, spikes plays an important role in decision making, and we already know that spike generation is a continuous and never stopping process. But there are numerous other myths about the brain that I may want to address, which includes people are either using left brain or right brain, or above all of that, that we are just using only 10% of brain. So if we are using just only 10% of a brain, then these scans should be like dark in the picture just because of the inactivity. So if we have a normal brain here, like this the brain these two images are from the like Alzheimer and the normal brain. So in a normal like in the Alzheimer disease who have symptoms of like memory impairment. So if you can see Alzheimer's, like one is the dark, and that is due to its inactivity. If 90% of the brain were not used, then 90% of the these inactivity brain tumors would cause like no problem at all. So while in a healthy person, the entire brain is constantly active and showing all these like red activity in the diagram. Even in the like when people are sleeping or regulating themselves, running, interpreting, reasoning, and while even listening to this talk like to this presentation also, we the human brain is always active. So this is like a totally myth that we are just using the 10% of the brain. uh, like the Alzheimer's, this in this picture also, they have like more than 10% of the brain they are using instead of all the inactivity and the damage caused. So, like after having a lots of research on spikes, there are some open questions which are not being addressed for human brain. So the most incredible thing is to me that despite of the discontinuous and like information flow in the brain, our conciseness experience is continuously and doing the all these things error free. We don't notice any like hindrance and missing holes in the world for doing all these activities. Neuroimaging techniques helping at a certain level, but theory from animal models still is not experienced on the human brain. Such of these questions are like how neurons are differentiating between the certain kind of information like language, math, music, etc. So we still don't know how the neurons are doing that. So now other thing is that why do we sleep and dream? What are the reasons behind dreaming, and are these dreams related to anything? And these neuroimaging techniques are still collecting, like we have the neurons activity at a group level, not on the single level, like single level neurons. So these are not being answered yet. And the other thing, as I told Dr. Shid, that human conciseness, it is still unexplained. So we don't know that what are the reasons behind those actions still yet. So in the end, I want to focus on a fact that like how brain have inspired the computers over the past decades, and engineers like have taken inspiration from the brain to improve the computer design. Our intuitions from digital computers break down for the brain, and like it is evident that the computer on which we are reading this, the computer obvious difference have a parallel nature. Now we have the advanced computers which having the cores, like different cores and GPUs and all these things. So these all are depend on the parallel processing of our brain, and like the multiple processes in single computer are uh, depend on the concepts from the neuroscience. Also, like in deep learning, machine learning, artificial learning, all is being like enjoyed great success, and it is depends on the mammalian visual system. And computer vision have taken all the advantages from that. These recent advances have expanded the area of the task to computer to capable of performing, but still the brain has its superior flexibility, generalization, learning capabilities than these computer things. So as the research neuroscientists can uncover all the secrets about brain, then we like computer engineers can uncover and advance the computer capabilities more. Thank you. Any questions?
Fantastic job, Deepa. You presented very well. You put in so much effort in making wonderful slides, narrated all very well. So I hope others can also emulate and learn from that. I have a curiosity question. I wonder whether you saw anything related to this question. How do we associate stimuli, which is so spikes or whatever that we get? Let's say I'm seeing an object, and how do I associate in the brain um, uh, conceptualization of that object? What does that look like? Does it look like sustained firing? So I have, suppose there is an object that I'm looking at. Object happens to be my phone. Does it uh, does brain recreate the conceptualization of this every time it thinks about it, every time it sees it? How would the thinking about the phone versus seeing it differ in terms of imaging in the brain? How does a stimuli, the process of thinking about it, manifest into conceptualization of that? How does the stimuli of looking at this object manifest into conceptualization of that brain? um, is the conceptualization uniquely created every time I think about it? How does it connects others information about the phone? For example, this phone happens to be Google Pixel 3. And then there are certain things I may remember about its capability or the lack thereof. How
Mhm.
is that recreated? Is it stored? So something along that line in terms of object recognition, manifestation, conceptualization
Yeah,
in the brain.
so author have mentioned several experiments on the animals, like when they are doing the experiments on rats. So they are checking like every time if they are giving a new information to the rats, what are the how are the spikes generated. So every new information have instant spike firing rate. So like a lots of spikes fires on the new information, while there would be like less firing on the old information which they have to remember. So one such experiment was done on the smell of cheese. So they are giving like small cubes of different cheese. So whatever like cheese is there, and they are trying to check like the spiking rate of those smell. So whenever there is a new smell, so their spike firing rate is very high, but on the like old smell it is not as the same. So I believe that whenever there is like new information is given to even to the human brain, so there are spike firing rate is high, while if like it is the old information that is being stored. So he explained the concept of dark neurons. So he believed that dark neurons, like the neurons which are silent, they are responsible for for storing the old information and learning new things. So they will fire when we have to like store a new information and learn concepts and all these things. So they have this particular task of learning the new information, the silent neurons.
Um, so does that imply that the brain stores information um, and recalls it? And if so, where would the brain store it? What is the granularity of storing the information? What is the granularity of manifesting it? How is it recreated from what is stored? Is it stored in bits and pieces and recreated, or is it stored as a whole with links to the properties kind of thing? I mean, what inspiration I can get about that? If it is storing, how much storage brain has to continue to store the information? If it is not storing, how does it recreate? From what does it create? What is the long-term memory? How does it become? What is the short-term memory? How does memory become long-term memory? Any things along that line?
Yes, so so long he discussed at a point about long term and short term memory. I remember that. So like the brain is the the complex structure, and it is like superior and generalizing through the feedback loops and all these things. So through the feedback loops we are like storing those information. And regarding the concept of like long term and short term, so if I do properly understand that concept is like for having a long term memory, first we have to something in the short term that can be there uh, for certain period, and then it moved to the long term like after reviewing that memory again and again. So these are the experiments they done on the rats and uh, monkeys. Yes.
So, any idea of how the information is stored and where?
No, I don't know. I have to look around it and research it a bit.
If I can comment, I think it's probably mostly stored in the synaptic weights, and short-term memory are probably mostly stored in the hippocampus, and then move to long-term memory in a more distributed fashion, probably in large part in more frontal part of the brain, but depending on the modality, if there's an information that is motor in nature. There will be some learning associated with the motor cortex.
Yeah. You know, one thing that is very interesting is that what might look like a seemingly simple activity actually is very complex and brings in many facilities. As an example, there are many activities we do, and you know, that may, for example, involve spatial consideration. You know, where are we in space gets used in amazingly broad variety of activity that we do, which may not consciously, you know, feel like, you know, we are in space. And a brain brings such a dimension very seamlessly, very effectively. I think that in, you know, if we, as we think about computerized options, there would be quite a bit of effort in ensuring that the spatial knowledge and experience is applied to something that you are doing, while, you know, brain brings that in, it uses in a very seamless manner, and the same applies to many other aspects of what we have. So the while there are brain areas are specialized, how one very you know, an area to really learn from is how different parts of the brain and different specializations are brought to bear in any activity that we undertake, any activity that humans do. That is also another massive strength that brain has, which we not figured out in computer architecture, in my view. You know, so while we may develop visual system, and while we start thinking about now multimodal AI, our conceptualization of different modality, of different aspects are still very rudimentary compared to what potentially happens, likely happens in the brain, how seamlessly it happens, how, you know, it get used. In that sense, that dense structure, massive interconnectedness is the thing that brain has that we don't have. In some sense, if you try to reduce this to a graph network, imagine creating graph with such a large fan out or fan in, and imagine the computational complexity of those things, right? All the graph algorithms break down when you talk about edge related computation, right? If you talk about node related computations, that's not hard. But the moment you have edges involved, computations break down because they're exponential. And somehow things happen in the brain where we might, what might require reducing that to an exponential algorithm in computational paradigm. In the brain, those seemingly exponential computations seem to happen, you know, with ease. So that's something I'm always very curious about, and try to see if there is any inspiration of how brain does this massively parallel, massively interconnected, you know, task in interconnected architecture, high interconnectivity architecture, and what it would mean to try and achieve something similar in computational system. Okay, wonderful. Really enjoyed. Anybody wants to else wants to ask question or say anything? While we are at it, Chaturangi, are you reading any book?
Dr. Shet, I was going to present the knowledge neurons paper. I don't know if time permits to present.
No, I mean, are you reading a book? My philosophy is for students to do all variety of reading, right? It's you have to read your papers, you have to read papers in related areas, and you have to read books, and you have to read news. You have to, if you want to be successful in future, in 5 years, you need to be a very different person if you're going to be really successful. The students who just end up writing a few papers and get out, they would have very narrow success. Students who can, who have really broadened their horizons and pick up a lot of different, reading, they, I've seen them to have become more adaptable, being able to have better social skills, all the things that it takes for broader success. So keep that in mind. I strongly suggest and ask my students to, continue reading. It could be fiction. It doesn't have to be science. It doesn't have to be health. It could be whatever it is but now is the time when you are in 20s to do that. It becomes too late after you are in 30s and start the job. So keep that in mind and try to, put something. Okay. All the, so I'll ask this question to Megha, Vipula, and various other people who are working with us and at early stage, to and pick up these good habits earlier on. I have shared very often articles that talk about how highly successful people are voracious readers. You take about Bill Gates or Musk or many of these people, they read very variety of things and so much of it. I wish I can do something like that, and I feel I've not done as well. But for you guys who are younger and I don't have so many distractions as somebody like I have, try to get there. So okay, well, fantastic. I'll meet my team tomorrow at 10. Talk to you guys. Bye bye. Enjoy.